Uh, Let us see dehydrohalogenation. Taking the vicinal halides, vicinal dihalides, then R dash. So this is a vicinal dihalide in the presence of base. Now H plus is abstracted, bond comes here, this will go off. We'll get a vinyl halide. R dash, then X. So this removal of HX is fast. We'll take the mechanism. Then again, using a base, H plus is abstracted, bond comes here, this will go off. Minus H. Hydrogen is going out without the bonded pair. Halogen with the bonded. So H in the form of H plus, X in the form of X minus. But this is slow. Now, this will give us alkyne. Now, if a geminal dihalide is considered, a geminal dihalide is the one that has two halogen atoms on the same carbon. Using this base, hydrogen is abstracted. Minus HX fast. Now, H, C, R, a double bond, then R dash. This is vinyl halide. Removing H plus, X minus. This, of course, is slow. Okay. Finally, we'll get alkyne. Now, let's see why the first step is fast and the second step is slow. what are the conditions for elimination? See, in the first step, elimination of HX is very easy because you are eliminating it from an alkyl halide. Alkyl halide which can easily lose H plus and X minus because considering both the mechanism E1 and E2, any kind of base is okay. I mean, even a weaker base is also okay for the first step, as you are removing a hydrogen halide from an alkyl halide. Whereas the second step involves the elimination of HX from a vinyl halide. That is the reason why the removal of, because when you remove a halide, I mean X minus, then of course you get vinyl with the vinylic carbon having a positive charge. Now, vinyl carbocation is highly unstable. We know that, right? So that is the reason why removing the hydrogen halide from a vinyl halide is difficult. So the second step of dehydrohalogenation is slow. Second step. Of dehydrohalogenation is slow as it involves the dehydrohalogenation of a vinyl halide. Okay, next. See, because this step is slow, or this step is difficult to carry out, it is carried out under extremely basic conditions. So, second step occurs only under highly basic conditions. Right. Then what are the bases generally employed? What are the extremely basic conditions employed? The regular bases what we use are alcoholic KOH. Of course, the second one is sodium amide. Even in these two also, KOH is a bit lesser basic compared to sodium amide. So with KOH, we go for a higher temperature because it is a less basic one when compared to sodium amide. We can go for fused KOH or alcoholic KOH at a temperature of 200 degrees centigrade. Whereas when we go for sodium amide or sodamide, this is of course a stronger base when compared to KOH. So a temperature of 150 degrees centigrade is enough to carry out dehydrohalogenation. We know that NH2 minus is a stronger base compared to OH minus. That is the reason why a temperature of 150 degrees centigrade is enough. Okay. Now let us take the mechanisms into consideration and see the interesting things. With the KOH, look at what happens. Supposing if we take this, with the say fused KOH, we'll consider the mechanism. So in this case, of course, we get RC triple bond CH. Okay. Whereas when the same reaction is carried out with sodium amide, see what happens. We need to take this in excess. On heating to a temperature of 150, we get RC triple bond C minus and Na plus. Of course, we get a hydrogen, but that is replaced by Na plus. But further on treatment with an acid, I mean in acidic medium, this becomes an alkyne. Okay. Now let us see the mechanism. Especially with the sodium amide. It is very interesting because sodium amide in general forms a terminal alkyne. Okay. A terminal alkyne, even if you start with a non-terminal one. Whereas fused KOH is generally used for converting a terminal one into non-terminal one. Let me give you the mechanism with KOH and sodium hydroxide. Taking this example, Let us consider isomers of Dibromo Pentane. Whatever may be the isomer, we have different isomers of Dibromo pentanes. When treated with fused KOH at a 200 degrees centigrade, finally we end up with Penta-2I. Let's see what are the different isomers possible for Dibromo pentane. Okay, we can take two this one. Okay, right. We can take even 3 also. Okay, next we can of course take 1 yeah, 1 Dibromo pentane. Then let us consider 1 2. So many are there. I think it's better if we just write this way. This is anyway 3 This is of course 1 then 1 2. Next of course I think 2 3. So many. 2 3 is possible. Even 1 3 is possible. Of course. Now any of these, whatever the alkyne formed initially, that is what I want. Alkyne formed initially rearrange to a more stable penta-2-ine. That is the interesting part. Say, suppose if you consider this case, you get a triple bond here itself. That becomes pent-1-ine. But even that also gets rearranged to a more stable penta-2-ine. That of course can be seen taking the mechanism. Whatever may be the isomer of dibromopentane, finally rearranges to penta-2-ine. Come on, let's take the mechanism. Now consider this alkyne. Okay. Let us see how it rearranges. using a base, abstract this. Bond goes towards carbon. Now this is when the interesting scenario arises. R, we have a hydrogen with this carbon carrying a negative charge. Now this negative charge is in conjugation with the triple bond. This is very interesting towards the carbon. So that is how it rearranges. Now we get RCH, then a double bond here, then here also a double bond. This is where we get negative charge. Okay. Of course, the base that has abstracted H+. Now this is how the carbene ion is resonance stabilized. Okay. After this, let us do this. Come on. This gives us R, C, then H, double bond, then again a double bond with this carbon getting a hydrogen. See, we got alene type structure. And this alene also undergoes resonance stabilization. I mean, just the movement of pi bond. Let me show that. R, C, H, double bond, C double bond, H, and then R. Okay. We have a B minus. Now, when this B minus is taken, the B minus abstracts this. Okay. As a result, we get, again, instead of writing it again, let me write it here. R, there is R, then C minus, right. Now this undergoes rearrangement. This one comes here, this one goes R, C, triple bond C, then okay, this will have a C minus, it has already got a hydrogen, and then R. Okay. Of course, BH is eliminated. Now from this BH again the same thing happens. Abstracted, and this will go towards the base. That's it. We will get this one. Compare the first one, what we have started with, and this one. You will come to know what has happened. Look at this. We got an isomerized alkyne. Check out the position of hydrogen. Okay. So whatever may be the alkene formed at the beginning, finally gets converted into the more stable pentatone in this way by undergoing different kinds of rearrangement. Ends up forming pentatone. This is what I wanted to show. See the mechanism. Now, let me give you the mechanism with the sodium amide. See, in this case, all the possible alkyne isomers or the triple bonded isomers finally get converted into terminal alkyne. Just like in the previous case, whatever is formed is converted into non-terminal or internal alkynes. In this case, we get a terminal alkyne because sodium amide is a strong base. Okay, all possible alkyne isomers initially formed deprotonate, lose a proton as sodium amide is a strong base. So finally, acetylide ion is formed. I'll show you that. On adding water to this acetylide ion, protonates, taking a proton from water. Protonates to form terminal alkyne. Okay. See this? It will be very clear. Now the NH2 minus, it abstracts this H plus. Okay, this gets eliminated as ammonia, forming the RC triple bond C minus. So then this with H2, I mean H plus and OH minus. Or else you can consider H3O plus. Gets protonated to form this as a major component. Now the thing what you have started with is one of the components of the mixture. Finally formed. When you take different dihaloalkanes, you finally end up with this acetylide ion. Now this acetylide ion takes a proton from water to finally form a terminal alkyne. So if you want to convert a non-terminal into terminal, take sodium amine. Let me take this example. Say this is oct-2ine. Now when oct-2ine is treated with the sodium amide at a temperature of 150 degrees centigrade, initially we get a terminal alkyne. Of course, that becomes an acetylide or alkynide of this type. And then we need water to protonate the alkynide form. So finally, we end up with this oct-1ine. Okay. So in general, sodium amide is used to convert a non-terminal one into terminal, whereas KOH is used to convert a terminal one into internal or non-terminal. This is all about dehydrohalogenation using different bases. KOH, sodium amide. Okay. See the details later.